Yeah, recording is started.
Okay, so the first talk today is by Omar Kidwai, and Omar is now at the Graduate School of Mathematical Science at University of Tokyo, and he will tell us about topological recursion and uncoupled Bps structures for hypergeometric spectral curves. Please.
Thank you. So thank you so much to the organizers for inviting me and also for just bringing us all together. It's nice to see you. I hope I see you guys in real life sometime. Okay, so this is based on a couple papers. There's one from last year on arXiv, and there's another one that should be coming out very soon, joint with Kohei Iwaki here. Okay, so basically the talk, I want to hopefully I just bombard you with this two formulas. There's two formulas I want to explain. You don't know what any of these symbols mean really, but the idea is that, okay, in the first formula here, on the left-hand side, I've got something that has to do with TR, and on the right-hand side, I have something to do with Bps structures that is basically a totally different formalism for computing things. And likewise, on the bottom formula, the left-hand side is something defined purely in terms of Bps in theory, and the right-hand side is something that you can talk about using only topological recursion. So just try to keep these in mind. It's hard, but I'm just going to try to explain all the symbols here. That's the goal. Okay, so TR, okay, we know and love TR at this workshop, so there's many fantastic applications of this thing. What's less familiar to people probably is the theory of Bps structures. So this is discovered from many different perspectives in physics and math literature both. So Gautam-Warnitsky studied 40 n=2 quantum field theories and made various constructions in hyperkähler geometry along these lines. Bridgeland came across the same things in his study of stability conditions. And Kontsevich and Soibelman also, their famous wall crossing formula is very closely related, controlling these Bps structures. And yeah, the theory of generalized DT invariance essentially follows this formalism as well. So both of these sides are very rich and related to a lot of different things, but they're really sort of distinct theories, and the flavor on each side so far in history has been a bit different. But our goal will be to relate them. And by the way, since the theme of the workshop is cluster algebras, I will say that Bps structures are related to cluster algebras in a well-known way. So if you want, yeah, that's my relation. Okay, so let X be a Riemann surface, which will always be for us P1. And sorry, I can't draw a diagram. So the rough idea of what I'm going to do, I'm going to start off with something called the quadratic differential on this surface, and I'm going to essentially, there's one thing I can do, which is I can take a so-called spectral cover of the surface P1, which roughly speaking is the same data as a TR spectral curve. It's not quite the same, but let's just think of it as about the same thing. And then there's two different paths I can take. I can do this whole Gautam-Warnitsky spectral network machinery, where I draw some graphs and I foliations, and then I count various degenerations, and I get a bunch of numbers, I get a bunch of homology classes, a bunch of stuff. But then I can also do something totally different. You know, these are both very sort of complicated formalisms for counting things, and I can do topological recursion instead. And I can spit out a bunch of other data. And naturally, the question would be, how can I relate these two things? So I started off with something, essentially one thing, and I want to know if I can go back and forth. And so we're going to try to answer that in the simplest cases. So what we actually do precisely is we prove the formulas that I wrote at the beginning for the example of the so-called hypergeometric quadratic differential, which is just this specific quadratic differential. So you can just think, so if x is a coordinate on P1, it's just, it's got two poles at 0, 1, and then a third one at infinity of second order. And on the top here, we have a quadratic polynomial. So there are two zeros and dx squared. So and then when I say hypergeometric examples or hypergeometric type spectral curves, I'll be referring to this example plus 8 other examples that come from limits and confluence of this example. So it's just, essentially speaking, it's a several list of examples that, yeah. So, okay, and what we do on a technical level. So first we extend the definition of BPS indices given by Gautam-Ornitsky to cover the cases that have simple poles, which we study, as well as degenerate ring domains. In the process, we have to compute the Bps spectra of these of the quadratic differential. So what that amounts to is we have to prove the existence and location and the description of all the saddle degenerations that happen in this quadratic differential's trajectories. And finally, we show that the so-called Voros symbols of a related differential equation solve something called the Bps Riemann Hilbert problem given by Ridgeland. So I'll say what all these words sort of mean later on, but that's what we do. And so the jargon that I'm using, I'm going to call my example spectral curves of hypergeometric type. And all it literally means is that it's one of these 9 examples. Again, the one to keep in mind is just the Gauss hypergeometric Q quadratic differential spectral curve. I'll call all these things hypergeometric type. So this is, keep this example in mind, but hypergeometric type just means these examples, and I think of them as genus 0 curves, hyperelliptic curves given by y squared equals q. Okay, so so we have a compact Riemann surface, and we can talk about meromorphic quadratic differentials on that thing. So that's just a meromorphic section of the square of the canonical bundle. And locally, what that means concretely is that you just have a function times dx squared. And I can talk about the zeros and their poles and all their orders and all these things. So that makes sense. And I'll call the collection of poles, I'll denote by P, and I'll call it the poles, and I'll call also the set of turning points will denote the zeros as well as the simple poles, because simple poles, turns out, play a similar role to zeros. So zeros and simple poles are called turning points. Now, given such a thing, given a quadratic—
You mean simple zeros, right?
Yeah, they're always taken to be simple. Yeah. I assume everything is a simple zero. So given a quadratic differential, I can do something. I can construct the spectral cover, which is a curve sitting in T star x. It's just given by, well, lambda squared should be the pullback of phi. So it's just a curve sitting in T star x, but then I equip it with a projection map, which inherits from T star x, as well as a meromorphic one form, which is also inherited from T star x. So it's the restriction of the Liouville one form. So altogether, these 3 things gives me a branched double covering of P1, together with a meromorphic one form that is smooth away from the preimages of the poles. Okay, and so now I want to do something with these things, but let me tell you what a Bps structure is first. So basically, this formalizes the structures that were found in many places describing DT invariance or the physics of 4-dimensional quantum field theories. So it's a tuple of 3 things. So I have a lattice, a charge lattice, gamma, which is a finite rank 3 abelian group, and which comes with an antisymmetric pairing into the integers. And then I also attach a number. So I have a homomorphism of abelian groups. So I attach a number to every lattice vector and give you a complex number called the central charge of that vector. And finally, perhaps the most non-trivial part is that I give you a map of sets that just assigns a rational number. In our case, it will be integers, assigns a rational number to every point in the lattice. And it has to satisfy the condition that it should give you the same thing if you take the negative. And there's a support property. It's some finiteness type condition. We don't really have to worry about it because it doesn't affect us. We're working in a very restricted case. So, okay, so there's some terminology that I'll use, which is that if omega is almost always 0, then I'll call the thing finite, a finite Bps structure. If the only time that omega is non-zero, those vectors are orthogonal to each other, then I say it's uncoupled. And finally, I say it's integral if it takes values in z rather than q. which it always will. So everything I study in this talk is a finite uncoupled and integral Bps structure. Okay, and so I'll call a Bps state or active class just any vector in the lattice that has non-zero omega, and a Bps ray will be the central charge of such a lattice vector. Okay, so finite uncoupled Bps structures and Bps states and Bps rays. Right, and we're only going to consider those. So one way to read Gayoto-Mornaitsky's work is to think of that they, well, among many things, one thing they did, they constructed Bps structures, and they provided a construction geometrically from the quadratic differential. So if we choose a sufficiently nice one, like in all our examples, so it's just q of x dx squared, and then I'll just let the tilde denote that I filled in all the simple poles on the spectral cover, sorry. So I can define now, so the lattice and central charge are not too hard. So the lattice I take is the homology classes of the spectral cover, and I just take the ones that are anti-invariant. So it's a sublattice of the homology. And the central charge, I just integrate the square root of phi. So yeah, it's just a period. And right, since in all our examples, the spectral cover is of genus 0, gamma is just a free abelian group, and the central charge you can compute very easily as in terms of the residues at the poles, and so it's just a linear combinations of the parameters that I wrote that are explicitly written in this Q. So okay, so gamma and z are pretty under control. So now, okay, we have to define the
Sorry, Omar.
Omega. Sorry.
Whether the rank of gamma is always even.
Sorry.
The rank of gamma, whether it is always even.
Well, no, it won't be.
It won't be. Okay, thanks.
No. Like, yeah, for example, if you take the hypergeometric itself, it's like a sphere with 6 punctures, sorry. So 5 generators, but then the anti-invariance projects it down to 3, rank 3 lattice.
Okay, thanks.
Yeah. Okay, so sorry, this should be a curly theta. Fix a curly theta, just a real number, and then I can define the foliation of that phase, which is just the level curves of this integral rotated. So yeah, so the imaginary part of this thing should be constant, and I'll call a trajectory of phase theta to be a maximal leaf. And so I can just plot these. I don't want to go too much into details, but I can just plot these. And for example, if I have a q of x is a quadratic second order pole with some residue r, depending on the value of r, I'll get pictures like this. So the greens here are theta equals 0, and the blues are theta equals pi over 2. And so basically, you can see most of the time things are spiraling into the pole, but at a very special value of theta, you will get compact leaves of the foliation, and that's useful and important for us in a second. So the other typical cases that appear, I have a simple 0 that looks like this. A simple pole would look like this. In black here, I've just written the ones emanating from the special point, the 0 or the pole. And if I have a higher order pole, the structure is always like this. So I have n-2 red arrays to which every curve in the foliation will asymptote. And yeah, so that's just what the structure looks like for higher order poles. And essentially, this is the unique local structure at every such point. Okay, so now there's it turns out we know from work of various people several decades ago that there's a 5 possibilities exactly for the trajectories. So whatever the 5th one is, I won't define it because it doesn't occur. So you can have a saddle trajectory which is when two, so the crosses here are zeros, the orange dots are simple poles, and the blue dots are higher order poles. So if I collide two turning points, if two turning points hit each other in the foliation, that's called a saddle trajectory. And if I connect a turning point to a pole, a higher order pole, then I call it a separating trajectory. And most of the trajectories, in fact, will be what's called generic. So they just go from pole to pole. So you saw that probably in the previous images. So most of these are all generics, and then I've singled out here the ones coming from the turning point. So right, and then there's one more possibility, which is that I could have closed trajectories, which you also saw. Okay, so there's 5 possibilities, four which occur for us, and we will. Okay, then we can define something called the spectral network, or the Stokes graph of phase phi, which is the collection of just all the separating and saddle trajectories. So I throw away most of the trajectories, and I just keep the ones coming from a turning point. So you can plot these if you want, and the example that you maybe one you can keep in mind is prototypical is the Weber differential. So it's just a quadratic polynomial. Most of the time it looks roughly like this. So you have, it's got this kind of structure where everything emanates and then goes off to infinity, but there will be some values of the parameter theta where you get a saddle trajectory going between two zeros, two turning points. Okay, so this is kind of like the structure that we're interested in. Okay, and so there's a fact, it's easy to see that every saddle trajectory or closed trajectory, actually, you can lift that thing. So these are all drawn on the base curve, P1, but I can lift it to the spectral cover in the following way. So I just give you, I don't want to get bogged down, but I'll just give you a picture. So if both points are simple zeros, both endpoints are simple zeros, then I just draw, I take the cycle encircling them, and I just lift it to the spectral cover, and that gives me a homology class up to sign. So every such trajectory gives me a canonical lift. And so now the so-called BPS indices omega of the differential phi are those that appear as canonical lifts of saddles in the spectral network. Except I have to add an extra part, which is that now I have to add or ring domains in the foliation. In the past, nobody did that, but we had to do that to consider some specific examples that appear in our work. So in some sense, the foliation is actually more fundamental. We should consider saddles and ring domains. Sorry. So I assign 0 to every lattice vector that doesn't appear as a canonical lift, and the ones that do, I give them a number depending on what the degeneration looks like. So type 1, 2, and 3 is just when I have poles or turning points hitting each other, and I assign them different values depending on whether it's simple 0, simple 0, simple pole, simple 0, or simple 0, simple 0. And then I have also ring domains, which by definition is just a region where I have compact leaves. And so if the closure of the region has one boundary component, I'll say it's degenerate. And if it has two boundary components, I'll say it's non-degenerate. So you can see here. And I just, again, I take the green curve here and lift it to the spectral cover. Okay, so yeah, so +1 and -2 here are well known from Gajotom-Warnayski and also from Bridgeland Smith. But we introduced +2, +4, and -1, generalizing this stuff because these degenerations appear in our examples and they hadn't really been considered before. So okay, so a terminology is the Bps spectrum is the corresponding Bps structure constructed out of this data. And so okay, so I told you a way to construct a Bps structure out of a quadratic differential, but I didn't actually tell you. There's a task which is to compute the image of this to find out what the Bps structure is corresponding to a given quadratic differential. And so what our task was to compute this Bps spectrum. The main technical thing was to show that a saddle actually exists when I have special parameter values. and the converse was actually considered by Okitanda, so we didn't have to worry about that. So the approach is to just, there's a couple, 1 and 2 are sort of, there's some restrictions that you can put on the Stokes graph, on the foliation. So there's a normal form. The pictures that I showed you essentially exhaustively give you the local behavior of the foliation around any turning point or pole. Sorry, I call those critical points. And there's another restriction which constrains the polygons that you can form out of the edges of the trajectory, sorry, whose edges are trajectories, called the Teichmüller lemma. So these two are sort of combinatorial constraints on what the Stokes graph could be. And then I use something called the horizontal strip lemma to finish the job. So what I do is first I use 1 and 2 to say, okay, there's only like some number of possible Stokes graphs. And then I'm going to use number 3 to rule them out. So what this lemma says is, if I have a region in my Stokes graph, sorry, in my network, in my surface equipped with the Stokes graph, if I have a region that looks like this, then the cycle that I've drawn here must have non-zero imaginary part. And so the idea is that all the possibilities I got out of 1 and 2 are actually impossible at certain parameter values of theta. So I won't go into any more detail in the proof, but that's what we successfully used to compute these. And so we can see, for example, here for the cell, we have a single degeneration, and we give it a -1 because it encircles a pole. So there's a bunch of closed trajectories in here. The main example is the hypergeometric, and so you have these 1, 2, 3 loops encircling a pole. So these are ring domains. There's a bunch of closed trajectories inside the loop that you can see, and then there's 4 saddles that go from a simple 0 to a simple 0. And so I give +1 to these 4, and I give -1 to these 3. And so that gives me the Bps structure associated to QHG. And then the reason I had to add the ring domains in was because of this Legendre example, where I have just 2 simple poles. And so what happens is I get at 1 parameter value, I get not only do the turning points collide, but I also get a ring domain around them. So this is here I've plotted the foliation as well in green, and so I get compact leaves surrounding the degenerate the saddle trajectory. And so I can lift both of these to the cover, and I get 2 different homology classes, and I assign them +1, +4, and -1 according to my yoga. So okay, so I'm low on time, so I don't want to tell you what TR is. You all know what TR is. So I take a Riemann surface with some functions, non-constant meromorphic, and in P1 I'm just going to take this Bergman bidifferential B is just going to be this specific bidifferential I've written here. So the zeros of dx are called ramification points, and the key to relating the 2 pictures is that we pick x and y satisfying the equation of the spectral curve, the spectral cover, which gives us an isomorphism between the spectral cover and this spectral curve from TR that I've written down. So yeah, I said they're roughly the same data. Now, Iwaki, Koike, and Take actually wrote down explicitly all of these spectral curves for the hypergeometric type differentials, and therefore we're able to apply TR to it, to all of them. And so, okay, so we know this is the formula for TR. I'm not going to tell you it again. I'm sorry, I'm low on time. But I construct a tower of multi-differentials, WGN, and what I'm going to care about is the free energy. So I take a primitive of ydx, and then I just take the residue of phi times WG1. So I only care about the WG1s, and I take some residue, and I do this over all the ramification points, and I get a number out of that, just a complex number. And so FG, the free energy is that number. And this is not, this is in previous work. So Iwaki, Koike, showed that they gave exact formulas for all of the hypergeometric type examples. And you can see now basically what the result is that for the hypergeometric, I have these 4 terms here, which and these 3 terms here, which, you know, that looks a little bit familiar. And the denominators actually, if you've spent enough time hanging around 4D n = 2 theories, you recognize that these are the central charges of the cycles that appear. So this has exactly the structure that I saw in my Bps spectrum. So I have a +1 here and I have a -1 here, so that matches up as well. And so the first result is the formula that I gave at the beginning, which is that the spectral curves of hypergeometric type satisfy this relation. So something purely TR on the left is actually equal to something purely BPS on the right. And this sum is taken over any half plane, a generic half plane. Okay, so that's the first formula. Now I'm very low on time, so I have to tell you everything in 5 seconds. Okay, so the Riemann-Hilbert problem, there's many applications of this thing, but Bridgeland and Gayoto-Mornitsky defined a Riemann-Hilbert problem associated to a Bps structure. This involves seeking functions of h bar, one for each point in the lattice, and I'm going to prescribe their jumping across the Bps rays. So to do this, first I define something called the twisted torus. So it's just maps, not quite homomorphisms, but twisted homomorphisms, just by -1 to the pairing of from the lattice into C star. And so then what I do is, if I have a nice enough Bps structure, I fix such a point. I fix a twisted homomorphism, and then for every non-Bps ray in the complex plane, I want to find a meromorphic, piecewise meromorphic map from the half plane centered on L into this twisted torus. And it's got to have the following properties. So if I have a sector, sorry, I do not have, I can't draw, but if I have a sector and its boundary rays are L1 and L2, so let's say that on the bottom right here, I've got L1 and slightly above it, I've got L2. So for every x gamma, I want the two functions to be related in the following way. So they're the same up to this jumping factor. And this jumping factor is given exactly by the Bps structure encoded. So I have the omega appearing here. So I take the product over everything inside the sector. So if I have L1 up to L2, and there's this sector here that I'm drawing, there will be a bunch of Bps rays, meaning the central charges of my non-zero omegas. And I want to take the product over all those rays. I want to take x associated to the gammas to those particular Bps Bps states, and then I want to raise them to the power of omega times the pairing. So yeah, the main point is that this jumping factor is a product over all of the Bps states that appear in between as you cross from one ray to the next. Right, and then there's prescribed asymptotics, which says that at 0, as I go to 0 in the half plane, the asymptotics are controlled by the central charge together with the fixed initial data that I chose. And then there should be tame growth at infinity, whatever. Okay, so now, okay. Iwaki, Koike, and Take constructed so-called quantum curves, which quantize the spectral curves of hypergeometric type. What that means is that basically I write down the topological recursion wave function, which is some h-bar series, some formal series constructed out of TR. Don't worry about the formula. It's just some particular formal series constructed out of these WGNs. And the integration is performed over a divisor that has a certain dependence on a parameter nu. And so if this thing kills, a quantum curve that is a differential operator that kills this wave function that has classical limits equal to the original curve. So I won't tell you the details in generalities. So I'll just give you an example so you can see. If I have the Weber curve here written down, and I pick some parameters, nu plus and nu minus, the corresponding quantum curve that they wrote down was the following. So this thing will kill the TR wave function with parameter nu. And so they did that for the other 8 examples. And now if I take that S that I wrote down, I take this formal series from TR and take its odd part, and then I integrate the derivative. So I can integrate it in 2 ways. I can either take a cycle on the spectral curve cover, or I can take a relative cycle that goes from a higher order pole to another higher order pole. So these two types of things, I can define a Voros coefficient for each one. And that's defined as the integral term-wise along either the cycle or the path from the pole to the pole. I threw away the first 2 terms here just to make sure that it converges or that it's finite. So this gives you a formal series computed explicitly by the former authors. And again, there's a similar formula to our FG for them. And so the punchline now is that if I do something called the Borel sum, which I hope most of you are familiar with, but so if I take a formal series, I can divide everything by n factorial to force it to converge essentially. And then I can take the inverse Laplace transform. And if I do those 2 things, I get a new function, which is actually, if all goes well, it's a piecewise convergent analytic function in H bar, but it'll jump when H bar passes certain rays. And its asymptotics are given by the original. So that sounds kind of familiar. That sounds sort of like what we're looking for. And thanks to the results of many before us, we're able to compute these Borel sums. Okay, and so okay, there's one little detail, which is that the pairing on the spectral curve, which is given by the intersection pairing, that's actually trivial. And so the Riemann-Hilbert problem I gave you is actually trivial. But I can fix it very easily by just so-called doubling the lattice, which means that I'm going to take now the dual, I'm going to add the dual lattice projected to the anti-invariance together with the new pairing, which is defined as follows. And this thing is actually non-degenerate. And so now I have a non-trivial Bps Riemann-Hilbert problem. Z and omega are just defined the same as before. I forget about the second factor. And so I can actually identify elements in this dual lattice with elements in the relative homology, so paths going from pole to pole on the spectral curve cover. And so finally, now I can define the final result, which is that if I have the hypergeometric type differentials and I have the quantum curve constructed by the previous authors corresponding to that, then the Voros coefficients, if I take their Borel sum, then I can actually solve the Riemann-Hilbert problem for the almost double Bps structure with an explicit constant term given in terms of the parameter nu. And so that's our second result. Yeah, that's essentially my talk. So maybe I can say just what other things we want to consider. So there's many other things to do. But yeah, okay. Questions?
Questions. So let's thanks first. Questions. One short question. I have a question. It's indeed short. So when you consider topological recursion, it has just one point, right? That was my impression. So to speak, you always consider just one branch point, which means
no. I mean, there would be two ramification points for some of the examples.
Ramification points. But you're on P1, right?
Yeah.
Okay.
But for example, the differential, for example, the hypergeometric one has 2 zeros.
Mm-hmm.
So yeah, so I don't think.
Okay. So interesting talk, and we are waiting for the second part or the first part tomorrow by Kahei. And let's thank Amar again.